Today's lesson focuses on diluting solutions. In a lab setting, it is very common to dilute solutions. For example, in a lab setting, acids are typically purchased in a highly concentrated solution because of cost. So it's more economical for us to buy a highly concentrated solution of hydrochloric acid or sulfuric acid and then dilute it down into whatever concentration you need. So because dilutions are so common in chemistry, we want to talk about this and understand a little bit about the theory and then the calculations involved. So when you are diluting, the number of molecules does not change with dilution. So an example is right here. So we have some sort of solution that has, as you can see, 6 little molecule atoms over here. And when we dilute, you can only make a solution less concentrated through dilution. You do not make it more concentrated unless you evaporate off the water, which typically is not done. So when we take a stock solution is what we call it. So this is the original solution. And then we want to dilute it. You add water to it and the volume is going to increase. The overall volume is going to increase. The number of moles or number of molecules does not change. Okay, so moles or molecules are constant. And when your volume increases, this is actually going to decrease the molar concentration of your solution. You have more water in there, so the number of moles per volume increases, and that is a reflection of concentration. The formula that we use for dilutions is down here where it says M1V1, or the initial concentration and the initial volume, is equal to the final concentration and the final volume. And this makes sense because if you recall, moles is calculated in solutions by taking concentration times our volume in liters. And this is commenting on the fact that the mole stays the same before and after dilution. So we're just using this formula here with 2 different variables because we're looking at a before and an after. In my opinion, the best way to do dilution calculations is to write down what you know on the side. And this is very helpful because you are dealing with the same variable. You're dealing with 2 molar concentrations, 2 volumes, so you need to keep your work straight. So it says a chemist starts with 50 mils of a 0.4 molar sodium chloride solution. So let's just write down, these are our initial amounts. So the molar concentration is 0.40 molar. The initial volume is 50 mils. And then we know there's going to be a second volume and a second molar concentration that we will be referring to. It says I dilute it to 1 liter. Okay, so my V2 is 1 liter. And it says, what is the concentration of sodium chloride in the new solution? So the new diluted solution. So when we look at this, we're going to set up our overall equation. So M1V1 equals M2V2, and we're solving for M2. So what we want to do is we want to get V2 out of there, bring it to the other side. We're multiplying that variable. We're multiplying V2 on the right side. When we bring it to the other side, we're going to do the opposite and divide it out. So we're going to have M2 equaling M1V1 over V2. Now, when we sub everything in, we need to notice that my units for volume do not match. And when we do a molar concentration calculation on its own, we need to have the volume in liters. But here, because we're going to be dividing out our volumes in our equation, it really doesn't matter what unit we have because they're going to cancel out anyway. So what I might do is I might just use milliliters here. It doesn't matter what you pick. It's going to cancel out, but you just have to make sure that you convert and that you're using the same volume unit. So we're going to put in our initial molar concentration of 0.4, 50 mils, and then I need to have milliliters in the numerator. 1,000 milliliters is equal to a liter. And setting it up this way, this allows my milliliter units to be canceled out. When I do my calculation, I get a molar concentration in my new solution of 0.02 molar. This is what the calculator says. Take a look at your sig figs. You need to have at least 2. So we need to put on another 0 there. And again, you can use units of moles per liter or just write a capital M for that unit. Here's another example that we'll try. It says, what volume of 0.2 molar glucose solution can be made from 50 mils of 0.5 molar glucose solution? So write down all of our variables off to the side, M1, V1, M2, V2. And again, we're looking for the variables that are before the dilution and then after the dilution. And this says, what volume of 0.2 molar glucose solution can be made? So these are all after dilution from 50 mils of 0.5. This is the before, okay, or the initial, however you want to call it. So as I look at this, deal with the initial first, let's do 50 mils here of the glucose solution. Initial concentration is 0.5 molar. After, they're making 0.2 molar. This makes sense, right? You add water, your concentration goes down, and they want to know what is the final volume that will be made. So we set up our equations. So M1 V1 equals M2 V2. We are solving for V2. We want to get M2 out of there. We're multiplying it on that right side. When we bring it to the left side, we're going to do the opposite calculation, divide it out. So we set up M1 V1 over M2. Sub in all of your values. So M1 is 0.5 molar, 50 mils. So again, I'm going to leave it as 50 mils, and that just means that my volume will have a unit of milliliters, and that is perfectly fine, unless they ask you to solve for a different unit. And let's come up with the final answer here. So when we calculate this, the final answer works out to be 125 milliliters. So this is what the volume of my final solution will be. And this now leads us to an interesting little thing about significant figures and volumes in a dilution equation. So if you look at the data that we have over here, I am supposed to round to 2 sig figs. And if I round to 2 sig figs, this answer, this is going to force me to go into scientific notation, and it's going to force me to round up to 1.3 times 10 to the 2 milliliters. And this is the only time that we do not round to significant figures in these chemistry calculations. And it is only with volumes, because it's going to give you the wrong volume. So if you were looking at this and you do this calculation, you're saying to yourself, I'm going to make a solution that is 130 mils, right? This is what that volume would be if it was expanded, as opposed to 125 mils. A 5 mil difference is significant because it's going to change this molar concentration. You're no longer making 0.2 molar. If you make a total of 130 mils, you're going to be even less, right? Because you're adding a bit more water, your concentration will actually go down a bit. So this is the only time, make a note for yourself here, that when you're solving for volumes in a dilution equation, you do not need to round to significant figures. Okay, let's do one more example, and we've got our variables already set up. Let's fill them in. What volume of water needs to be added to 45 mils of 1.32 molar sodium sulfate? So here are my befores, okay, or my initial amount. So let's get those down. 45 mils is my initial volume, 1.32 molar. I usually use capital M. Sodium sulfate. To obtain a solution, so this is now the after, with a concentration of 0.95 molar, we are asked to solve for the final volume here. So we're going to set this up. So V2 is equal to M1 V1 divided by M2. Let's sub in our values, 1.32 molar times 45 mils. We're going to divide by 0.95 molar. And once we calculate that, we're getting a final volume of 62.53, I'll say, milliliters. Okay, and remember, you are not going to round to sig figs with volumes. But the thing is here, this is not the final answer because it's saying what volume of water needs to be added. So this here is the final volume of my solution. I need to figure out how much water. So I still have to do, I'm going to number, right? Because I have to do a second step. My volume of water is going to be the difference between that initial volume of stock solution and this final volume of the diluted solution. So what we want to do is we just want to take V2 minus V1 and then come up with the amount of water. So I'm going to take 62.53 mils. I'm going to subtract off 45 mils of stock solution. And when I do this, I'm getting a volume of water of 17.5 mils. We'll round to one decimal place. Again, you know, we should be aware of significant figures. And right here, you know, this is only, it has no decimal places. So if I was going to round this, I would be saying 18 mils of water needs to be added. And you can't do it because if you round up the volume of water, then that molar concentration is not accurate when you make it at the end.